So this is a similar philosophy to bifurcations, but it's not a bifurcation problem, although there are bifurcation questions associated to it. But I just want to talk about what we know about existence of periodic orbits near equilibrium points. So recall so if we have some imaginary eigenvalues of L, non-zero, let's say, no, I'll say simple at first. Then you get a normal mode and the normal mode is the two-dimensional eigenplane. Let's give a name to this vector space Rn or V, R2n. So two-dimensional, this doesn't have to be Hamiltonian. Two-dimensional eigenplane with periodic orbits to period 2 pi over omega, right? That's just first year undergraduate differential equations. So that's sitting maybe some large space, and you've singled out one pair of eigenvalues which are imaginary, and you get this inside the space. If they have multiplicity, then you certainly get some of these, but it depends on whether the have the same on right, because the solution is general solution to the linear differential equation. So when you put t equals 2 pi over omega, the fixed points will be, well, it's just that. But the point is it's always non-zero, and it's even dimensional. So it's non-zero if 2 pi over omega is, if omega is an eigenvalue, or I omega is an eigenvalue of L. But this might have some nilpotent parts, so the kernel might not be the same as, I mean, there's a geometric eigenspace, algebraic eigenspace dichotomy. So that was general, nothing to do with Hamiltonian. So now suppose we take a Hamiltonian system which has okay, so I want to ask about periodic orbits in the nonlinear system, not just in the linear system. So the linear system is easy. That's the answer. So the theorem of Lyapunov, so about 1905. Maybe 1905 was the translation and the Russian was in 1895. Anyway, around that time. He proved the following. So he has this condition on the sort of non-resonant condition. So I omega is a simple eigenvalue, plus or minus I omega, but integer multiples are not eigenvalues. Then there exists a smooth surface in V, where the dynamical system is, the Hamiltonian system is, tangent to the so the normal mode is this eigenplane, so it's a linear subspace. So now we have a curved surface, possibly curved, tangent to this plane, which consists entirely of periodic orbits of period close to 2 pi over omega. Okay? It's not going to be constant. So imagine a pendulum. So we know the period of a pendulum is 2 pi square root of L over G, I think, or G over L, L over G. Period, yes, 2 pi root L over G. But that's approximate. It actually depends on the amplitude. So, but for small oscillations, it's very accurate. And that's the idea here. So the period varies as you move out. It might get shorter, it might get longer. Examples of both. But it's, as you get smaller and smaller, as you tend to the equilibrium point, the period tends to 2 pi over omega. So the picture, the nonlinear picture in the phase space looks something like this. So So there's the linear subspace. And then tangent to that, so period is a function of amplitude. As amplitude tends to 0, so period tends to 2 pi over omega. That's what this means. So that's Lyapunov's theorem. So it requires, firstly, simple eigenvalues, and secondly, this non-resonance condition. So Lyapunov himself, he proved it just for analytic Hamiltonians. He assumed it's Hamiltonian, but again, like I said at the beginning, there have been lots of proofs of this theorem using all sorts of different techniques and some different conditions on the smoothness. But certainly, I think C2, maybe even C1. So it certainly doesn't need to be analytic. So, generically, you would expect equilibrium will have several imaginary eigenvalues, and each, so this is what we call a nonlinear normal mode. And each will be simple generically and non-resonant. They will not be integer multiples of each other generically. And so there are, let's say, I omega k. There are k nonlinear normal modes. One for each of the eigenvalues. So you imagine the space, large dimension space. There are lots of these. Oh. So, two things I want to say. First, before we start the symmetry story, so a note, important note in all this. If, remember L was always J times a symmetric matrix, and this is actually the Hessian matrix, maybe 1/2. No, Hessian matrix of the Hamiltonian. No. If S is, So it's a symmetric matrix. The Hessian is positive definite. So that was the condition, Lagrange-Dirichlet condition for stability.
Excuse me. So what means similar 2 pi over omega? Is it mean topologically conjugate?
No, this is just a number. The period.
Or higher order
now? So, you know the picture of the phase portrait of the pendulum? Yeah?
Oh.
So the period for the linear approximation is 2 pi,
Okay, I see.
right? But if we move out, it changes a bit. The period gets longer. So it's not equal, but it's approximately equal. Yeah. But as we move out, the period tends to infinity, so it increases. If we think of the spherical pendulum, there are periodic orbits like this, and as the amplitude increases, the period gets shorter, because you think of it, if it's almost horizontal, it has to go very fast. So the period is small. So sometimes the period can increase and sometimes it can decrease. So this is approximately equal. This is the definition. It's a continuous function of the amplitude. So if S is positive definite, then all the eigenvalues are imaginary. So everything is about oscillations. And that's because, like a Hamiltonian system, I haven't mentioned this before, but I'm sure you know, the Hamiltonian is preserved. So if S is positive definite, or the Hessian is positive definite, then the level sets of the Hamiltonian are spheres, or ellipsoids. So the motion cannot have a real unbounded part. So the eigenvalues can't have a non-zero real part. So they're all imaginary. They might be zero, of course. Oh no, if it's positive definite, then in fact they're all imaginary non-zero. But if it's positive semi-definite, then they could be zero. But they could not have a real part. Yeah, that's right. So typically, generically, you would have, if we're in R2n, we would have n different eigenvalues, and so you'd have n different families of periodic orbits that look like this. So it's a good theorem. Then you might you can go further and talk about maybe approximate integral system and K-M theory and have invariant tori and things like that, but I'm not going to go in that direction today. Yeah. But what happens when we relax these two hypotheses? So maybe not simple and maybe allow resonances like this. Well, Lyapunov's method says nothing. People looked at examples and for a long time, and In different cases, they proved different things. So there was a famous study of the 1 to 2. In R4, you have plus or minus I and plus or minus 2I. So for the plus or minus 2I, that's okay. You can use Lyapunov's theorem because there are no integer multiples of 2I. But for the I, you don't know. Is there an eigenvalues? Is there a normal mode? Nonlinear, other periodic orbits? It wasn't known. Well, eventually, it was found that there are. Gastamat proved it. Well, other people maybe before, but he gave the best proof. Maybe the first proper proof in the 1970s. Then Weinstein proved a remarkable theorem. Nowadays he does Poisson geometry and category theory and things, but then this was quite hard analysis. Topology and analysis mixture. So he proved that if this quadratic, this Hessian, or S, to it, is positive definite, then on each energy level, so you fix the energy near zero, there exists at least n periodic orbits. Okay. What he didn't say is anything about how these periodic orbits fit together in smooth families or anything. So this was a variational approach, calculus of variation. So you fix the energy, and there's some functional, and you study some topological properties, like Morse theory, but it was quite... it's a difficult paper. It's in infinite dimensions. Anyway, he proves that this functional has at least n critical points, but he can't control where they are. It's just a topological thing. So it has n critical points, and those correspond to n periodic orbits. So you don't have this nice picture with the amplitude varying or the energy. You can parameterize these by amplitude or by energy, because the energy is increasing out. So just to emphasize, it does not assume eigenvalues are simple, nor no assumption, except this one, and probably C2 or something, I can't remember. All right? So, this is a least bound, right? Then there may be many more. We don't know. All he could prove is that there are at least n. And if there's no resonance, then you have n, precisely n. One for each pair of eigenvalues. One for this, one for n of them. So that's what you expect. But in the 1 to 2 resonance, there are 3. Periodic orbits. So this means if eigenvalues are plus or minus I omega and plus or minus 2I omega, then there is a nonlinear normal mode of period two pi over 2 omega, okay, for this one, because there's no multiples of this. But we don't know about this, but calculations and some tricky proof. And there are 2 families of periodic orbits of period 2 pi over omega. So but they don't form smooth. Actually, the geometry of them is slightly different. So this one is a nonlinear normal mode, so it looks just like that. Nice smooth family. These other ones, they form a cone. That's a cone inside R4, so it's not clear. But, well, so you have this, and then you have the smooth so this looks like R3, but it's really R4, so you can't really judge too much from that picture of what the geometry really is. But so on each energy level, you've got 1 blue one and 2 white ones, so you see 3. Whereas Weinstein's theorem says at least 2. So it's complicated in general. People have studied some other resonances. So Dalstomate studied a lot of different resonances. But what about symmetry? Oh, no, before I say that, let me just say something about what the setup for proving, well, one way of proving Lyapunov's theorem, or what I'll talk about afterwards. So, this is a variational problem. So we're going to define a functional called S, parameterized by a parameter. I want to call it tau. So we've got our space where the dynamics is taking place, and we take some loop U of S. Right? So that's some C infinity, well, I've written C infinity here. You can never do functional analysis on C infinity, so CK. You get it the right way around. So if we write it in terms of Q's and P's as common in Hamiltonian systems, so this should be ds. P so there's something missing. I have to put the tau in, and I have to get it in the right place. So that's got Q dot. So I think the tau is here. So this is a functional on here. Right, so it's just a smooth, I mean, it's a function on here. And the lemma so S1 is the reals modulo 2 pi, just like the unit circle. So think of S as the angle, little s here. So U is a, or U, so it's a critical, so we have periodic solutions if and only if critical points of this function will give me periodic solutions. So tau tells me, so this has period 2 pi, u, by definition. So the period of this is 2 pi over tau. So tau is like omega. So maybe tau is not in the right. So u dot gives me a tau. Yeah, that should be right. So the aim, I'm not going to go any further. I just wanted to say what the setup is. So the variational approach is to produce some argument that says you have to have a certain number of critical points of this functional under certain conditions. So that's the setup, and that's all I'm going to say about it until I. Okay, so now symmetry. So this causes eigenvalues to be multiple. Multiplicity, to have, English, multiplicity greater than 1. Except for the very simplest cases of the group of order 2. But as soon as you have anything like dihedral group or cyclic groups or things, then the multiplicity is always going to be bigger than 1. So one would never be able to apply Lyapunov's theorem. One can apply Weinstein's theorem, but it doesn't tell us a lot. So. Let V omega So let's start off with one of these irreducible symplectic representations. So all the eigenvalues are equal because it's irreducible. If they had two different eigenvalues, then I'm assuming it's got imaginary eigenvalues. If it was two different ones, then each eigenspace would be invariant under the group, and that's not possible because it's irreducible. So this has eigenvalues plus or minus I omega. With some multiplicity, depending on the dimension of V omega. So you can choose a basis because it's no, well, I won't use that because I don't want to prove that. Now on this space V omega, we define an S1 action. So if you think of L like this, then it's clear, but it's also clear like this. So two pi over omega let's call it theta. No. Yeah. So, exponential of 1 over omega theta L, so theta in or 2 pi z again. So this has period 2 pi, because L, e to the theta L, or e to the TL has period 2 pi over omega. Do I mean omega theta? 2 pi over omega, no, that's right. So actually symplectic. So this is an action of the circle on the space. So one common way of writing this down is to use complex notation. So if V omega it's always symplectic, so it's even dimensional, so you can make it look like CR, then L is multiplying, you can identify this matrix with multiplication by I. So no, e to the I theta. So it's just scalar multiplication in the complex because L looks like omega I in the usual. So if we treated this as x plus iy to make it complex, then L would be omega times I, and so 1 over omega is just L is just I. So it's e to the I theta, the usual complex multiplication in a circle. So you've introduced that action just by calculation, by using the linear system. So we have a representation or an action. We're given the group G that's acting, symmetry group of the problem. And we've got this new bit S1 and the two commute, so we have a representation of G cross S1. And computations with this are quite easy because G is, you're given some matrices, elements of G, and S1 is just, if we think of it as complex, then S1 is just scalar multiplication. So the symmetric version of Lyapunov's theorem tells us the following. Proving this theorem that I started thinking about Hamiltonian systems. So it's a few years ago. Right. So I'll give an example in a minute, a couple of examples. So sigma is going to be a subgroup of here, of this group. So the less than sign just means a subgroup rather than an arbitrary subset. So sigma is acting. So we want to say, what's the subspace of points that are fixed by sigma? Well, if it's 2, then there's a nonlinear normal mode. So a nice smooth surface, just like before. A smooth surface populated by periodic orbits with period close to 2 pi over omega. All right? And symmetry sigma. So what do we mean by symmetry sigma? So the nonlinear normal mode is just this picture. It's tangent. So normal mode was tangent to Lyapunov's mode. Now it's tangent to this fixed point space. So, as I said, I'm going to do an example in a minute. But let me just say what do we mean by symmetry of a periodic orbit? Maybe actually the example now would be better, and then the symmetry is clear from the example instead of writing down formal definitions. So a simple example with symmetry, mechanical example, would be imagine a mass. These are 3 points, and you could attach the mass to springs. Okay, so this mass can move around subject to these forces of the springs. The springs have spring constant and natural length, and then there's the size of the triangle. These are all parameters that you can vary, but this moves according to the forces. One can write down long expressions for the potential energy, but I won't do that because we can apply the theorem without any knowledge of the explicit Hamiltonian, just a couple of assumptions. This has D3 symmetry, the symmetry of the equilateral triangle by construction. The springs are identical, and they're at the vertices of an equilateral triangle. So if we swap the springs over, or if we move this point to the point below, the potential energy would be the same because you've just exchanged the lengths of these two springs. So,
there are some assumptions about the G action. Assumption?
it has to be symplectic.
Oh.
Yeah, and linear. So it's, yes, linear. It's a representation, symplectic representation. Yeah. G has to be compact. Yes. So finite, usually. So, so there's an equilibrium in the middle, and we assume it's stable. So it depends. If you put springs which push instead of pull, then maybe it's unstable. It depends on the parameters. Minimum. Mass in the middle. So we can apply this theorem. So this is symplectic. So this is just R2, but the phase space, of course, has got R2 for the configuration and R2 for the momentum, so it's R4, but it's symplectic irreducible. So it's a symplectic irreducible of real type. So the linear system is just so the Hessian is just a scalar multiple of the identity. Four by four identity. So this is 0. So the period, let me make my life easier by having c equals 1. So the period is 2 pi, the natural period of the system, of the linear system. So we have an action of d3 cross S1. And I'm now going to think of R4 as C2. So it's the same matrices, the usual matrices for D3. Now we think of them as acting on C2 instead of R2. And then, so let's take a point Z. So that's what we want to find out. Yeah. That's what it means to be fixed. So what's this? This is G e to the I theta Z equals Z, or GZ e to the minus I theta Z. So that's just an eigenvalue problem for G. So it's easy calculation. First year linear algebra. Okay. So what are the, if we take elements of G and D3, it's either rotation by plus or minus 2 pi over 3, okay, that way or that way, or it's a reflection in one of, like the horizontal line, reflection in that line, or that line. So eigenvalues plus or minus 2 pi I over 3 for this one, or plus or minus 1 for reflection. So there are lots. So suppose G is that rotation. Let's call it rho. Okay, then we can combine that with an eigenvalue. Or plus or minus, it doesn't matter. Fixes Z equals, well, what is it? It's something like 1 e to the 2 pi I over 3. Something like that. I can't do the calculation in my head. But anyway, there's a vector that it fixes, that's the eigenvector. Might be a sign wrong. I'd have to write down what the matrix is, work it out. So what this tells me is that, so this is it's an eigenvector, an eigenspace for the 2x2 problem. It's a one-dimensional complex eigenspace, or two-dimensional real eigenspace. We want the fixed point space to be two-dimensional, so that's exactly what this theorem is helping us with. So the dimension, the real dimension of the eigenspace is 2. So what does it look like? Well, what's it telling us? This combination of rotation and the eigenvalue. So if we go back to, this was why I introduced this setup, this functional, there's a natural action on u of this 2 pi over 3. What was u's argument s? So how does a group element act on u? It takes s. So this is a function of s, and it is u of s with the translation minus 2 pi over 3. So the point is now, so this is in the proof, you have to identify critical points with periodic solutions. So we've done this eigenspace calculation. This is telling us that there are critical points, and then the critical points are periodic orbits with this property. So this was the last bit. I wrote that they have symmetry sigma. Sigma is the group generated by this element. So that's equal to u, because it's fixed. So rho u of s, well, equals so this is telling us that the motion, so suppose we start here. Two pi over 3, so this is period 2 pi, so 1/3 of a period later, it's got by rotation. So if we rotate that, it goes to here. Let's see if I can draw something convincing. So the point the theorem is saying is that this periodic orbit has triangular symmetry. Right? So if you rotate it, it's the same as changing the argument by 2 pi over 3. So the symmetry of the periodic orbit is what is... so that's how this object is moving. It's moving in some... Well, for the periodic solutions, where was the equilibrium here? It's moving in something which has got some triangular symmetry. It doesn't tell you more than that. The other possible subgroups with two-dimensional fixed point spaces could have reflections in them. So a reflection like this. The reflections have eigenvalues plus or minus 1. So if you combine it with +1, it means it's fixed. So there's no change in phase. So if we're using this reflection, it means that the solution is lying along this axis, which is not surprising. It's an axis of symmetry, so you would expect If you pull the mass to the right a bit, it will move back and forth just along that line. But more surprising is if you use the -1 eigenvalue, then you'll get motions that do something like this. Symmetric. So you also get periodic motions where the reflection is a change of period by half a period. Sorry, that last bit was a bit rushed, but this is what the theorem is telling us. It's about not just the existence of periodic orbits, but their geometry or their symmetry as well. Okay, shall I stop there for a break? And we'll resume in 15 minutes for the last hour, if you can still survive. Any questions?
So now this story is on linear space. The dynamics.
This is local. This is local.
Linear. So on global, the critically is given by principle of symmetric critical.
Yes, well, that can help. That can help, but the principle is in here in this proof as well. So, yeah. So this is a sort of global construction, but this argument is all local in a neighbourhood of an equilibrium, right? So it doesn't tell us about periodic orbits' global existence. Geodesic problems, for example, periodic orbits on an ellipsoid or whatever, nice questions like that. This approach doesn't immediately say anything because it's local. So for the last hour, I'm going to talk about some actual systems, well, point vortex system. With lots of geometry. We'll probably see some of these bifurcations occurring and so on. Okay? So should we have 15 minutes pause?